Hey, what's up guys? And today we're going to talk about changes in thermodynamic state properties for enthalpy, internal energy and entropy. I'm going to assume you know the first law, second law, Maxwell Relations, and derivatives of thermodynamic properties. I'll put some video links in the description so you can see. So previously, we've derived the thermodynamic properties for constant composition or single component systems. This is the one for enthalpy. Del V, del T, keep P constant, plus V dP. Alright. We also did it for internal energy. du equals to cv dt plus t del p del t, keep volume constant, minus p dv. Yeah. And our two expressions for entropy were, firstly, as a function of pressure, ds equals cp over t dt minus del v del t p dp. Now the other one is a function of temperature and volume, cv over t dt plus del p del t v dv. Yep, so that's what we have so far. So we are going to do all of these for an ideal gas. And why is it so important? Well, ideal gas is a good benchmark for measuring changes in thermodynamic state properties. Ideal gases are easy to calculate and it's quite easy to conceptualize, right? So like for example, if I want to teach you about liquids, I'd start with the most common example, which is water. I'm not going to use honey or lava or syrup. I'm going to use water first, tell you a little bit more about water, and I'm going to say honey is like water except stickier, and lava is like water except much hotter and more viscous. So for thermodynamic properties, our equivalent of water will be the ideal gas. And we are going to use it to benchmark against real systems. So we can say ideal gas is like a real gas, or real gas is like an ideal gas, except enthalpy changes with pressure or something like that. So now we know why we are doing it. Let's begin. So for ideal gas, PV equals to nRT, or we can write it as PV bar equals to RT, where V bar is the molar volume. Yep. Right. And what's next? Well, we can see the derivatives here we need to calculate. Del V, del T, keep pressure constant for these two. And del P, del T, keep volume constant for these two. So, for the first two, what is volume for an ideal gas? V bar, or just V, for ideal gas equals RT over P. And the pressure, of course, equals to RT over V bar. Right? Some textbooks, they like to just use use V instead of V bar to like not confuse people, or it's messy, but it's kind of roughly the same thing, yeah? So let's do with dH first. dH equals to Cp dt plus minus del V del T P, keep pressure constant with temperature times temperature plus V, put dP there, right? So del V del T P will be this, equals del by del t. Alright, what's v? V is RT over P. Keep P constant. Right? We can see it a bit properly. It's differentiating with respect to T, keeping pressure constant. So if pressure is constant and R is constant, you can take this part out. And what you're left inside is just this. And this is just 1. Right? And the other derivative we need to evaluate will be this, del P, del T, V. Keep V constant. And that is similar. So you're differentiating with respect to T, R, T over V. This is just V bar, yeah? I'm just not writing the V bar there. It's the same thing. So, if V is constant, R is constant, because you're keeping V constant in this case, what you're left inside is quite similar. Del T, V, which is just 1. R over V will be your derivative here, and R over P will be your derivative here. And so we can substitute that back into our equations. So dH equals to Cp dt plus minus T. The first one here will be R over P. Alright, and you plus a volume here, dP. Well, this is actually RT over P, right? And that is just ideal gas volume. Ideal gas volume, right? So essentially what we are saying is dH equals Cp dt plus volume minus volume dP. So that's how people say, or that's how people get dH equals to Cp dt. Now we will notice a similar effect holds true for the internal energy. Du equals to Cv dt plus temperature times R by V minus P dV. Alright. Then this is RT over V, and that is just pressure. And that will be equals to pressure minus pressure. I'm not going to write everything out again. So it's just Cv dt. So for an ideal gas, du equals Cv dt in any case, and dH equals to Cp dt. Alright. For entropy, that's rather simple. Cp over T dt minus R over P dP. Alright. Because what we started with was del V del T, keep pressure constant. And what we've derived is del V del Tp is just R over P. That's why we're getting this here. And similarly for the second one, ds equals to Cv over T dt plus R by V dV. Remember, this is molar volume, yeah? Alright, so we are more or less done for this. Yep, so hope to see you soon. Thank you.